Hello. Yesterday we did some exploration with Desmos and we were exploring exponential functions. Today we're going to look at that a little bit more formally and put some vocabulary with it and see where it's going to be used. This is a really useful skill that shows up in a whole lot of areas. So it's really important that we talk about this. Exponential growth functions, or you can just say exponential functions, and then there are two types of them. There are growth and there are decay functions. Growth means it's going up over time. Decay means it's going away over time, getting less. So they're all going to have this basic format. They're going to look like this. They're going to look like y equals a times b to the x. So the reason these are called exponential functions is look where your x variable is. Do you see how it's up in the exponents spot there? So they're like, the variable's in the exponent. What should we call this? Exponential. So there you go. Exponential functions. B is the base here. Now, that's not going to be a variable. B is going to be a number that you will get in the problem, okay? Sometimes you'll have to figure it out, but it's not something that's a variable. X and Y are your variables here, okay? A and B are just standing for unknown. So B is our base number here. It's what your exponent is attached to. And that base number is for growth functions. The b is going to be greater than 1. Okay, so we'll talk about that. We'll compare it when we talk about decay functions another day. So for growth, the b value is going to be greater than 1. Now a here is going to stand for the initial amount. Remember, the word initial is the beginning amount because, think about your initials are at the beginning of your name. So the initial amount, how much you start with, that's going to be your a value. Okay, and again, that's going to be something that you get told in the problem most of the time. Okay, so let's graph one of these. It's going to look like, so if you have a piece of graph paper, cut a little square of it and tape it in your notes here. And we are going to start with a real basic graph. We will start with y equals 2 to the x. Okay, so my base here is 2. My x is in the exponent spot, so that's why this is an exponential function. Wait, I didn't put something that would be an a value. What would the a value be here? What is multiplied? Well, I don't see anything written out front there. Well, that would be an a value of 1. But so I don't really need to write that 1 though, so I'm just gonna leave it off. So y equals 2 to the x is a real basic exponential function that we can graph. So if you don't know what a graph is going to look like, your best strategy is to just start choosing numbers for x, filling them in, see what you get for y, and then plot those points and see what happens. So let's go 0. So if I take that 0 and put it in for the x, what's 2 to the 0 power? Not 0, it's 1. Anything to the 0 power equals 1. What if I put a 1 in for the exponent? 2 to the first is 2. What if I put a 2 in for the exponent? 2 squared is 4. What if I put a 3 in for the exponent? 2 to the third is 8. Careful, it's not 6. 2 times 2 is 4 times another 2. 4 times 2 is 8. What if I put a 4 in for the exponent? 2 to the fourth, that would be 16. There you go. So we're doubling, we're doubling, we're doubling, we're doubling. That's what's happening here. So I think that's far enough. You'll run out of space anyway in your graphs. But I want to put some negative x values in and see what happens with those. So I'm going to just, since I want to keep this y equals 2 to the x on the screen, I'm just going to make another little table here where I'm going to put the negative 1 in for the x. So if that negative 1 is going right up here for the exponent, 2 to the negative first power. Do you remember what negative exponents do? Yeah, they make fractions. They make you take the reciprocal of something. So if 2 to the first is 2, 2 to the negative first would be 1 over 2. So this would be 1/2. 1 over 2. If I put a negative 2 in for my exponent, 2 squared is 4. So 2 to the negative second power is 1 over 4. If I put a negative 3 in, since 2 cubed is 8, 2 to the negative third would be 1 over 8. It's the reciprocal. Put a negative 4 in for x, that would be 1 over 16. Okay, so we have all those values. Let's take them and graph them. So let's see. Get a little graph to pull up here. I think I better go with a small one so I have room to graph a lot of this. That's probably too small. How about medium? Yeah, that'll work. Okay, 2 to the 0 is 1. Let's see, I'm going to put dots like this. Happy face, okay. 2 to the 0 power is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. Okay, I'm running out of room that way. So now I'm going to go with the negatives. 2 to the negative 1 is a half. 2 to the negative second is a fourth. I should go back to just dots. 2 to the negative third is an eighth. 2 to the negative fourth is a 16th. So I'm getting a picture. It's looking something like this. So that's not exactly the best purple curve that I've drawn there, but you get the idea of what's happening with these. So I want to talk about the end behavior of this because it has something interesting going on each end here. So let's go to the right first. So on the right, as I go to the right, what happens to these y values? Well, they skyrocket. They go up really, really fast. Exponential growth means that things are growing very rapidly. Okay, so that's what you see over on the right side. Now on the left side, you see how the curve, the fractions that we're getting smaller and smaller. Like a half is small, but a fourth is even smaller. And an eighth is even smaller than that. And a 16th is even smaller than that. And the next one would be 1/32, and that's even smaller than that. So they're getting smaller and smaller and smaller, closer and closer to 0. But they're not actually going to ever be 0 because 1 over something is always something. It's approaching 0, but it's not equal to 0. Do you remember that we had a word for that back when we dealt with rational functions? Starts with an A, asymptote. Yes, this has an asymptote on the left side here. So let's do some labeling, I think. So over here, we'll call this an asymptote, asymptote. And it's as the x's approach negative infinity, the y's are approaching 0. Remember how that's how we read end behavior. It's getting closer and closer to 0, but it's not touching it. Now on the right end over here, for this end behavior, we could say as x is approaching infinity, x's go left and right. Positive infinity would say I'm going to the right. Okay, so that's how you say mathematically I'm going to the right. So as I go to the right on this graph, what do my y's do? They skyrocket. So the way to say that is you say the y's are approaching positive infinity. So there's your two end behaviors. What would the domain on this be? So let's say I wanted to see this. Let's add another page. Okay, so what would the domain and the range of this be? Domain is your x number. So how far to the left and how far to the right does this graph go? Domain. And this could go forever in both directions. So we can say that this domain is from negative infinity to positive infinity. Now what about the range? Range is your y, so I want to know how high it goes and how low it goes. And we name the low end first and then the high end second in our parentheses. Or we might need brackets, depends. So like the square kind. Anyway, how low does this exponential function graph go? Well, it's getting close to 0. So if I look on the left-hand side of this graph, it looks like a plane coming in for a landing, and the runway is the line where y equals 0. So it's coming in for a landing that way. And that's the lowest it's ever going to go, but it's never going to hit 0. So I'm going to use the regular style parentheses to show it's never actually going to get to 0. If it got to 0, I would use the square ones, okay? But it doesn't get to 0, so I'm going to use the round ones. Now, the easier part of this is how high does it go? Well, it goes up forever. That is infinity. So there's your range. Let's see, what else should we talk about with that? Well, that's probably good for that. So exponential functions will have this basic shape to them. Let's look at where we might use this. Let's say we were going to look at the number of germs on your hand. Okay, so germs have been a big thing lately. So let's say that you start out with, we'll say just 5 germs are left on your hand after you washed your hands. You did pretty good, but you know, probably can't get every single germ off. So we'll say we start with 5 germs. And we should probably call them like bacteria or something, but we're just going to call them germs. And we're going to say that these germs, they have a doubling rate. They divide, so that every 1 germ or bacteria, whatever, will become 2. And we'll say that they do that every half hour, okay? So you wash your hands, we'll say 7 o'clock in the morning. So we'll look at our time here and our number of germs as our y value. So it doubles every half hour. So at 7 o'clock, we've got 5 germs on our hands here. At 7:30, how many germs would we have? Those 5 germs, they all divide, they become 10 germs. At 7, or no, that'd be 8, sorry, half hour. 8 o'clock, those 10 germs, they all divide. Now how many you got? Oh, you got 20 germs. Not too bad. So now 8:30 rolls around. Now how many germs you got? They double again. Now you're at 40. By 9, what do you got? Yeah, you're at 80 germs. By 9:30, you're up to 160. Okay, so that's getting kind of bad. 10 o'clock, not lunchtime yet, is it? You're going to be up to 320 germs. Whew. 10:30, you'd be at 640 germs. You double it again. By 11 o'clock, oh man, we're at 1,280 germs. So we've broken 1,000 now. At 11:30, still not lunchtime. Oh man, we'd be at 2,560 germs. 12 o'clock. Oh my goodness, that would be 5,120 germs. And 12:30, that's when a lot of us eat. So let's see, it'd be at 10,240 germs on your hand from those 5 that were there. And that's not even counting it that you picked up any during the day. That's just counting the, is that mitosis? I think that's mitosis process of the germs being on your hand. So how many of you wash your hands before you eat lunch? Let's do that, shall we? So in this case, the reason I wanted to show you this example is those numbers, they were getting really big, right? Weren't those getting bigger than the first example I showed you? This is still an example of doubling, so my base here would still be a 2, but there's a little bit of a difference because how many germs did I start out with here? Well, I started out with 5. So in this case, my equation would look something like this. Y equals 5 times 2 to the x. The 5 is the initial amount. So I wanted to show you a number where I had an initial amount here. And x here would be in like half-hour units. I probably should have clarified that a little bit because it was every half hours how often this particular germ doubled. So there's that. But sometimes things don't necessarily double. They're growing, but they're not like doubling super often, they might have a slower growth rate than that, and we often describe that with a percent. So let me show you how else this can look. If we use a percent, so if we use a percent to describe growth. Today we're talking about growth. You'll see the same idea though show up when we talk about decay. It would look something like this. So y equals a times 1 plus r to the t. So a is still going to be your initial amount. That is exactly the same. R is going to be your rate. So this is often given as a percent. So these are particularly going to show up in financial situations, like if you get interest in a bank account or something like that, they will give that as a percent. But when we go to do math with it, we need to put it in the decimal form. So if it said 2%, you would write a 0.02 for that rate. Okay, so you would take the percent, change it into a decimal. Let's make a note there. Change the percent to the decimal. Remember, you move it over 2 spots. There you go. That's when you plug it in. Oh, now let's talk about that 1. 100% is how much you start with. Like the original amount would be 100%. So if I had to begin with 100% of something, what's the decimal form of 100%? Move the decimal over 2 spots. That would be 1. Okay, so 1, if you start with that original amount, 100% of it, 1, and add to it, it's going to grow. Okay, tomorrow we'll see decay and we'll subtract from it, and that'll make it shrink over time. Oh, that leads me to the T up here. T stands for time. And yeah, it's like the X. It's your independent variable here. It's just almost always time that we're describing something growing over time or decaying over time. So there's that. So let's do an example of something like this. Let's say that we have $1,000 in an account that gets we'll say 3% interest. Okay, so could we take those facts and see where they would go in this equation? What would this look like if I was plugging them in here? So how much money do we have to start with? That would be the $1,000. So that $1,000 is going to go in place of the A. So I'm going to have, let's see, I'm going to have y equals 1,000 times, now the R, I want my R value so I can fill in the parentheses here. What is my interest rate that I'm earning on this bank account? That would be 3%. Okay, so now we have that as a percent. So 3%, move the decimal over 2 places, that would be 0.03. So 1 plus a 0.03 is what we would have right here inside the parentheses. So 1 plus 0.03, I'm going to write that as a 1.03. And that's the base of my exponential function here. And then t is time. So I'm going to put a t up here. I haven't asked you a question with this yet. I've just given you some facts. I haven't actually asked you to find anything. So let me say, let's figure out how much money you would have in 10 years. So you could just take that 10 and plug it in for the t and do the math. I want to show you how to use the graph to go with this. Okay, so I'm going to go over here. Oh, I thought I had it up. I guess I don't. Desmos. So let's graph the function y equals 1,000 times 1.03 to the, I'm going to put an x in there so Desmos understands what I mean. Can't see anything right now, so I'm going to zoom out a bit. so I can see it. Oh, I don't want to zoom out that way though, do I? Okay, here we go. I think I said 10 years, didn't I? How much money will I have in 10 years? So years would be on your x-axis. That's where my time is. That's my independent variable. So I want to go where the 10 would be and go up to where the red curve is and see if I click. Okay, that's 9.8, 10.5. Okay, I'm going to do it the cheater way. I want x equals 10. That'll give me a gray clickable dot. Okay, so look at the y value of that. See that $1,343.92? That's how much money you would have in the account. Let me ask a different question about this situation. So I've got this $1,000, put it in this bank account, makes 3% interest. Now I'm wondering, when will this bank account have $2,000 in it? When will I end up with double the money that I started with? $2,000. So if I want to end up with $2,000, which axis would be labeled with dollars? Is that the x-axis or the y-axis? Well, it's not the x-axis, that's time. So the y-axis is telling me how much money I have. So I want to know when the y value is going to equal $2,000. It's going to be somewhere about here. I want the y value to say 2,000. So to make it easier, I'm going to put y equals 2,000 so that I get that clickable gray dot. Okay, so it looks like it would take 23.45 years for me to get double the money that I started with. So you can use the graph to figure out those values. So I think that is everything that I need to tell you. So, nope, it's not. I need to give you a little bit more vocabulary. So we can talk about growth rates and growth factors. So in this problem, the 3% was my growth rate. Okay, that was the rate at which this paid. So growth rate here is the 3%. The growth factor, sorry, I was burning supper. So we have a growth rate, that's the percentage that they give you, and then a growth factor. Factor means you are multiplying. So in this, the 1.03 is what you are multiplying by over and over and over again. Remember, an exponent tells you, hey, multiply by this over and over and over again, however many times I tell you. So the growth factor here is the 1.03. It's that entire base. That's the growth factor. So it's the base. So it's connected to the growth rate. It's just that you have added it to the 1 if something is growing. You start with 100% of it, and then you add the rate. That tells you what your factor will be, what your base is. And tomorrow we'll see that as decay. So, okay, I think that's everything. So remember that Jesus loves you, and so do I, so do your math.